All right, so yeah, the first half, okay, I have to make myself being able to share. Sorry about that. The first half, I prepared some slides about the last topic that I mentioned that we are able to cover. Again, this is about differential privacy, how to do that together with synthetic data. And the focus is on how we can, yeah, how we can get the, how we can get microdata, okay? So part of this, well, I don't really have demo code because all of the methodologies are pretty complicated and advanced. And since this is the last lecture, just want to give you a overview of how things work. And the details, as you will see, some of them are actually still being developed. So it's hard to tell, like say, compare all of these methods and which one is better and all that. But still, I want to tie differential privacy together with synthetic data, and this time about micro level data, that the ones that we have been working on for the majority of this course itself, as well as for your final project. But we are trying to make, say, synthetic data that can satisfy differential privacy. Okay, so a couple of things for the introduction. You remember about the differential privacy approach that we talked about, right? The definitions, the implications, and the Laplace mechanism, okay? And here, the particular key terms, definitions, I would say, that you will start to see again in this lecture is the sensitivity and the privacy budget, okay? Epsilon and delta F, okay? So here we have this delta F with the subscript F, because this is about query, right? Remember back then we defined F as the query function, and then any kind of sensitivity is the L1 norm of the query function itself. So we have this subscript of F, okay? And in today's lecture, you will also see that we'll have privacy budget, so epsilon is always there. That's how we spend the budget in terms of the differential privacy approach. But we're also gonna keep talking about sensitivity, okay? So here, as you will see today, we do not define it as delta F anymore because we're not working with query, okay? Or we're working with micro level data, right? That we're trying to release through the synthetic data approach, which also satisfies differential privacy, okay? Last week we talked about this, okay? So this is based on the Differentially multinomial conjugate models that we talked about, well, a few months ago, I would say by now. And we're working on tablet data, right? We're using the Differentially multinomial model itself. Differentially is conjugate to the multinomial sampling model. And then we specifically saw that, well, we proved it, albeit really quickly and maybe not so much in detail last time, that in order to make this Differentially multinomial conjugate model differentially private, we had to satisfy that requirement by making the minimum of alpha I, which is from a prior, right? It's the hyperparameter here, satisfying this particular condition that is highlighted in red, okay? So if you do that, you're able to generate, right, count vector Y star satisfying the differential privacy definition, okay? So this, as you can see, is, well, back then we had to figure out how alpha can be playing a role in all of this together with epsilon that we're trying to use the definition of differential privacy to prove that this will work, okay? All right, so moving to today, we focused on respondent level data, okay? And like I said earlier, it's the focus of our synthetic data approach and all of your projects as well. And just want to mention that all of the work that you've been doing, synthetic data that you're generating, you will have certain levels of privacy protection, right? We talked about how to get identification disclosure, as well as the risk that we can compute, and the attribute disclosure and the AR risk that we can compute. So it's not that synthetic data does not provide privacy protection, it does. But as we have been doing, and you have been seeing that it does contain certain levels of privacy protection, but it does rely on the knowledge and assumption of what the intruder knows, right? Whereas differential privacy, as you know, is starting from the bounding idea that if two data, I should say, if two databases are very similar to each other, like differ about one record, we want to bound the output, right? The ratio of the output by a certain upper bound that does not go above that. In particular, that's how the privacy budget epsilon goes into it. So the original definition that we cover in the first round is in equation 3. Okay, that's when we have this curly M here that indicates any kind of mechanism. Okay, last time when we started talking about in the context of tabular data, synthetic tabular data, remember we introduced this equation 4, where we have y star as the synthetic count, right? And then y and x, they are the two databases that only differ about one record, okay? And theta is the parameters in the model. Epsilon, again, it's the privacy budget, okay? So today, when we're working with synthetic microdata, we're also gonna follow equation 4, okay? Obey, I won't be able to cover the proof. This will be too much more complicated to do. But I do want to show you that how Bayesian thinking can come into play when designing any kind of synthesizer or synthesis model that we have learned or we have heard about to make it satisfying differential privacy. Okay, so to get us started, I have to first introduce you a new mechanism. It's called exponential mechanism. Okay, the short story is that the exponential mechanism can turn a non-private mechanism into a private mechanism. Okay, so you can think of a non-private mechanism as, say, a Bayesian synthesis model. Okay, maybe the one that you're fitting, it does provide privacy, right? But it does not provide privacy according to the definition of differential privacy, so we call it a non-private mechanism. Okay, so you can think of a Bayesian synthesis model, let's just say like a simple linear regression that we did with the synthetic CE data that we did. Oh, that is a non-private mechanism. And the exponential mechanism, we will see soon, that it can turn something like that into a private mechanism, say the same Bayesian model, but satisfying the differential privacy guarantee. Okay, so it sounds a little bit vague, but bear with me, the exponential mechanism can turn can turn one non-private mechanism into a private mechanism if we can lay out all of the work. Okay, so I'm going to show you what the exponential mechanism is and then how it is being done. And then I'm going to mention 3 different mechanisms based on the exponential mechanism that they proposed different mechanisms based on the word, the names that you can see here, and how they construct their mechanism based on the EM. We call EM as the short for exponential mechanism, and how things work there. Okay, so will be a high-level introduction lecture. It might not be as interactive as what we had been doing so far in this lecture, in this course, but hopefully we'll still give you some idea.